All right, let's get started. I'm going to start with a few questions. So how many of you think that there are way too many container runtimes out there? Okay. How many of you think that there should be a single container runtime for all your workloads? Okay. And how many of you think that there should be as many container runtimes as possible for all the types of different workloads that you have? Well, not that many. How many of you don't care? Okay. All right, so hopefully I'll talk about all the container runtimes, and you get an idea of all the container runtimes related to Kubernetes, and also some other runtimes. The motivation behind this talk is this article that I came across last year after KubeCon, and it talked about all the different container runtimes that started showing up in the market due to the container runtime interface from Kubernetes. And also there were some comments about what about these other container runtimes like Mesos and OpenVZ? So I'll talk about those as well. So a little bit of background. I work at Branch. We run containers pretty much everywhere. We run all of our API services in Kubernetes in all the different types of environments, QA, development, and production. Lots of different languages. We service about maybe 60 to 70,000 requests per second. And then we run all of our data pipelines and Flink and Spark frameworks used on top of Mesos, also in all the types of different types of environments. And then we ingest maybe about over 10 billion records a day, and over 10 billion queries, real-time queries a day. So the runtime that we use, the primary runtime, is Docker Containerd on top of Runc. And there's still some databases and some big data apps that have not been containerized yet because we think they're not ready for containers yet. So they're stateful type of applications. So disclaimer, where do runtimes actually live? So a lot of you probably already know, but the Linux kernel has all these facilities that make containers possible, like to instantiate the containers, to run the containers. So those facilities are namespaces, C groups, AppArmor, SELinux, SECOM, Linux capabilities. So everything that the containers do is on top of that. So a little bit of what I'll be talking about, the history of containers, some of the early container runtimes, then some of the containers for Kubernetes. And then I'll talk about which ones you might want to use depending on the type of workload. And then I'll talk about the future of container runtimes with respect to the Open Container Initiative and the Container Runtime Interface. So in 2002, kernel namespaces became available in the Linux kernel, and that's the first feature related to containers. Then in 2006, OpenVZ was created so you could run containers, but you needed a kernel-level patch, so you needed to create your own kernel image, boot up your server, and run your containers with that specific kernel image. And then in 2007, another feature related to containers became available in the kernel, and that's C groups. Then in 2009, Mesos started as a research project at UC Berkeley, and that was the first implementation of C groups in user space. Then in 2011, LXC became the first standalone container runtime. Then in 2013, Docker became so popular, and they came out with the first release, and the first release was based on LXC. So in 2014, they said, OK, LXC is not providing all these different things that we want to do with that the kernel supports. So we're going to write our own library called libcontainer. So they released Docker libcontainer on top of libcontainer. And then in the same year, Rocket became available as an alternative to Docker. Then in 2015, the people the communities from Docker and Rocket got together and they said, we need to work together to come up with some standards. So they came up with the Open Container Initiative. And then Run C, which led up to OCI, is the first OCI compliant runtime, started work in 2014. Then in 2016, Kubernetes, or the Kubernetes community, came out with CRI, Container Runtime Interface, because they had to do a lot of modifications to make Rocket work on Kubernetes. So they said if there's any new container runtime, they're going to have to implement this interface. And so Kubernetes doesn't have to care, what it needs to call out in the back to run containers. And some of the CRI shims available are CRI-O, Rocket for Rocket, Fracti for VMs, and CRI Container D. So what does it look like now? It may seem something like this. I mean, you have all these different containers going all over the place. You don't know where it's going. Everybody's creating its own container runtime. So it's a little bit spinning. So the landscape looks like this. So you have OpenVZ by itself. Then you have LXC also by itself. Then you have Mesos with its own containerizer running on top of AppC, and then also Mesos supporting Docker and possibly supporting OCI in the future. And then you have Kubernetes with all these different runtimes and shims, Rocket, Docker, CRI-O, and CRI-O can run C or Kata containers. You can run Kubernetes to a Docker shim and run another OCI compliant runtime. So it's a little bit confusing. So let's talk about OpenVZ. So first released in 2005. So it's a kernel level patch. You have to patch up your kernel, boot up your server, and you could run containers. One of the interesting things about OpenVZ is that it supports live migration. Carryover from the virtualization world, where you could have a container running on a machine, physical machine, and live migrate it to another machine in real time with potentially no downtime. And some of the cons is that, of course, you need to create your custom kernel, and OpenVZ 7, which is based on RHEL 7, the word in the community is that it's not as stable as OpenVZ 6, and OpenVZ 6, or RHEL 6, happens to be running a pretty old kernel, 2.6x. And of course, there's no Kubernetes or container runtime interface integration. So let's talk about Mesos. So Mesos' first implementation of C groups in C++. It's got pretty good performance. It supports Docker, AppC images. And it potentially will support OCI, but the word is that they'll latch on to whatever Docker does. So the best use for Mesos is kind of like Spark and Flink frameworks for big data applications. Not that it cannot be used for other types of things, but the containers are particularly good for those. And the cons is that you can't run these containers outside Mesos. So you need the Mesos framework to make these containers run. So let's talk about LXC. So this is the first time, or I came across containers myself, and this is what the main LXC page looks like in 2012. So up until then, everybody was talking about virtualization, and then so I came across this page that said like, oh, this is a new approach to running lightweight virtualization, and it's using C groups and namespaces. And it's supposed to be much faster than virtualization. So in summary, LXC, its nickname is chroot on steroids. It's got pretty active community, right? So there's active development going on right now. Its main components are LXC, which is the actual runtime written in C, LXD, which is a daemon that manages your containers and your images written in Go, and LXFuse, which manages the file system. Is it OCI compliant? No, it's not OCI compliant. But the word is out there that they're working on an LXC run that will be OCI compliant. I couldn't find a lot of information on LXC run, but I was able to dig something up, and that's what it looks like. So some of the downsides is that it's got its own image standard, and There's not a lot of adoption. There's some people using it, but it's not widely used. And there's no Kubernetes integration yet. It's a work in progress. There's some tickets open in the community, but they haven't been prioritized. Let's talk about Rocket. So Rocket supports 2 types of images. It's just a single process runtime, RKT, Rocket. Is it OCI compliant? No, it's not OCI compliant. It's still in development. They're planning to do it through something similar to Runc. What's interesting is that the people who worked on Rocket also worked with Docker to create Runc, but they didn't get around adding complete OCI compliance to Rocket. And it's got some unique features like support for trusted platform modules, TPM. And you can run some workloads in isolated VMs, and it also supports SE Linux. This is how you run Rocket with Kubernetes, aka Rocknetis. So you would just start your kubelet, and you specify your container runtime to Rocket. So some of the pros, it works out of the box with Kubernetes. It's got this pod-based semantics that is very similar to Kubernetes. Just a single process. It supports KVM to run workloads. It supports Docker, app-C, maybe OCI in the future. And some other cons is that CoreOS, a company behind Rocket, just got acquired by Red Hat, and they're not so focused on runtimes that much anymore. They're more focused on Kubernetes distributions. Rocket, the project that is supposed to implement the CRI for Rocket, is still under development, and there's not a lot of adoption in production. Some people are using it too, like LXC, but it's not massive. And their standard image format, app-C, is not, it's no longer in development, so they decided the OCI is the future, but they haven't gotten around supporting it. So let's talk about Docker now. So the first name was just Docker, and now it's all these different things. So you have Docker daemon, Runc, Containerd, and the CRI Containerd. So the CRI Containerd just recently, a couple of months ago, became just the CRI plugin, and the Containerd daemon handles your storage, your imaging, your networking, and it takes care of instantiating your containers. So this is what it looks like in the old days. This is from the main Containerd page. You have Docker managing your storage, your imaging, and your networking. And then on the new Containerd 1.x, you have those functions moved into the Containerd daemon, and Containerd still instantiates the containers. Okay, so let's talk about CRI now. CRI is just an interface. It's not this Containerd, CRI Containerd, or the CRI plugin, so that's a little bit confusing. But just CRI is just the interface introduced in 2016 so that Kubernetes can talk to multiple runtimes. And it's just a gRPC interface, and the shims are available, are CRI-O, Rocklet in development, Fracty to run VMs, and like I mentioned before, the CRI plugin. So this is what Containerd looked like maybe 2 months ago. You had an extra daemon, CRI Containerd. The kubelet would talk to it using gRPC, and then this daemon will have an image service and a runtime service, and then would talk to another daemon called Containerd through gRPC, and that daemon would instantiate all the pods and the containers. A little bit confusing. So this is what it looks like now, that maybe from a month ago. So now you just have a single daemon. Your kubelet talks to CRI to the plugin, to the CRI plugin, and then it has an image service, a runtime service, and the same daemon takes care of instantiating the pods and your containers. This is how you configure Containerd with Kubernetes 1.10. You actually don't have to configure anything because the default runtime is Runc. But if you want an untrusted workload runtime, you can configure that, and it could be something like Kata containers or clear containers. You can also specify another runtime instead of Runc if you don't want to run the default. And this is how you start Containerd. So just a system start your daemon, and then you start your kubelet with saying that your container runtime is remote, and you point it to the Containerd daemon. That daemon, you point it to the socket. So that socket is listening gRPC and CRI. And then you can also set it up as a systemd service in the kubelet, that is. So some of the pros, it's very widely adopted, very stable. A lot of companies are using it. Pretty good performance is written in Go. The community is pretty big. There's a lot of commercial support, a lot of companies behind them, running in thousands and millions of environments. And one of the interesting things that they're working on is Windows containers over Windows and Linux containers over Windows. And some of their cons is that the runtime, meaning containerd, is very coupled with the daemon, the containerd daemon. So when you restart the containerd daemon, all your containers get restarted. And some people say that's not a big deal because a lot of times you run your workloads in Kubernetes, and then Kubernetes starts your containers again on the same machine or a different machine in your cluster. And then another con is that the standard packaging has way too many daemons because it also has this Docker daemon on top of containerd and your Docker shim that keeps your container up and running and your containerd daemon. So in the new packaging that I'm not really sure if it's out there, the daemons will be reduced to 3 in Kubernetes. And of course, another con is some naming confusion between CRI, CRI containerd, and yeah, so. Let's talk about CRI-O. CRI-O is just a shim. It's not an actual runtime. It's just a shim that allows Kubernetes to talk CRI to another container runtime. So its nickname is CRI-O, like cryogenics, like the logo. And the main components is CRI-O daemon that is very, very similar to containerd. It handles the storage, the imaging, the networking, and the kubelet talks CRI to it. It has this other component called the common daemon that is very similar to the Docker shim that keeps your container up and running. And this one monitors your container. This happens to be written in C. And is it OCI compliant? Yes, it is OCI compliant, and you can run runc or any OCI compliant runtime. And this is what it looks like at a high level. You have the kubelet talk gRPC to the CRI-O daemon, and the CRI-O daemon instantiating your pods and your containers. And each container being monitored by this common daemon. And this common daemon is managed by systemd. So this is how you start CRI-O. You would CRI-O daemon, and then very similar to containerd. You specify your container runtime to be remote, and you point it to the CRI-O socket that is listening gRPC, CRI. And some of the pros is Kubernetes ready. It's got great performance. It's written in Go. There's 3 daemons by default packaged for Kubernetes. And this common daemon that I mentioned is written in C. It actually monitors the containers. So whenever you restart CRI-O, your containers don't get restarted as opposed to containerd and Docker. So it's restart safe. And it's extendable to other runtimes. And the cons is that it just went GA recently, and not a lot of people are using it in production. You cannot run containers outside Kubernetes, but there's this tool in work in progress, and I think the Red Hat booth is demoing this tool. And so if you're interested, you can find out more about it. It's called Podman. And there's no default for image management as well, but they also have another tool in the works called Builda. Or you can also use third-party tool like Scopio or Umochi, which are OCI image management tools. Let's talk about crun. This is another runtime. So when did it start? It started in last year, 2017, by Red Hat. It's mainly implemented in C, and it's got the best performance. Is it OCI compliant? Yes, it is. And the downside is it's just pretty new. There's not a lot of adoption, so it's a work in progress. These are some benchmarks from their page. So if you run 100 times bin through with no new network namespace, it's about 40.7% faster than runc. If you run the same with new network namespace, it's about 16.5% faster. Now let's talk about Kata containers. When did it start? It started last year by the OpenStack Foundation. Its first release is slated for next month. So what is it? It's two projects getting together, RunV and Clear Containers. So RunV from Hyper.sh and Clear Containers from Intel. And basically, what they're trying to do is run containers in VMs. Their main implementation is in Go. The security is supposed to be the best isolation. You're just running completely isolated in a VM. And is it OCI compliant? Yes, it is OCI compliant. So this is what it looks like. You have RunV and Clear Containers. So Kata is supposed to support both of these types of environments where you run Fracti or where you run it with CRI-O, and CRI-O runs another container runtime, which in this case is Clear Containers, but it will be Kata containers. And this is Kata with Docker in comparison to Runc. So you see that it's not very much different. So it's pretty much the same. You have your Runc at the bottom, and you just plug in your Kata runtime at the bottom. And this is configuring Kata with Docker, and pretty simple. You're on your containerd config.toml. You say the runtime is Kata. And this is Kata with your containerd CRI plugin, and you specify your untrusted workload runtime to be Kata. Kata in Kubernetes, so you see, or OCI compliant runtimes. So you can see you can use any CRI shim, like CRI plugin, just got renamed, or CRI-O, or you can use Fracti, or you can use this Docker shim, and then you can run Kata in the back. And this shows Kata running with CRI-O and alongside a trusted workload that will run with Runc, and an untrusted workload that would run with Kata inside a VM. Kata and CRI-O, you just change or add this to your configuration, to CRI-O.conf. You point it to the Kata runtime binary, and you specified your workload trust to be untrusted. And this is Kata with Fracti. So you start out with your Fracti daemon, then you start your kubelet, and you say remote container runtime, and you point it to the Fracti socket. And then you restart this Hyper-D daemon that is supposed to, or Fracti is supposed to talk to manage the virtual machines. And then, so the Katas, the pros are that it provides great isolation. It's got the best security. It's got good performance, not the fastest, but good performance. The VMs have been around for quite a while, so they're pretty stable. And you could potentially use like stateful type of applications, like where you attach your storage to a VM, and maybe you want to attach that in an encrypted fashion, or maybe you want to store some security information, some database security information. Might be pretty useful for those type of applications. And some of the cons, you need a bare metal machine. So a lot of the cloud providers have VMs. So AWS just recently announced bare metal machines, but they're still in preview. So like, we have an account, and we haven't been able to have bare metal machines on AWS. And I tried to run this on C5 instances, but I wasn't able to run it. The C5 has the new KVM hypervisor. Supposedly that you could run nested virtualization, but I wasn't able to run it. And there's some issues with the startup time, but there's a couple of features from that the Kata community is working on, like VM templating and allowing your VM to start up with no firmware. And for now, it's actually slower than something like Runc. So other notable runtimes, so there's a bunch. So there's an NVIDIA runtime, and just specific to GPUs, and it's a modified version of Runc, and it talks to this NVIDIA container, and it's written in C, and then it talks directly to the GPUs. There's also Railcar. It's an OCI implementation in Rust. There's Pouch, Alibaba's runtime. It's just a shim that uses Runc in the back. There's systemd nspawn, and it's a very lightweight isolation mechanism, not quite like a runtime. It just provides some namespace isolation. And there's Let Me Contain That For You from Google, and that got open source in 2015, but it's no longer being developed on because they're focusing more on OCI runtimes. So a brief word on unikernels. So a lot of people, there's been a lot of buzz about unikernels, and people have said, oh, this is the next best thing after containers. So it's not really clear that's going to be the case. So people are saying that once you instantiate your unikernel, you cannot reuse your memory. There are no tools to debug, like where's PS, htop, or top. And you have to learn maybe specific languages that come prepackaged with your unikernel. And the ones currently available are some like Haskell, OCaml, and Erlang. So you have to learn those languages if you don't know them. So, I mean, they're sort of popular, but they're not as popular as the mainstream languages. So what do I use now? So if you want stability, stick with Docker. Containerd code base has been around for 4+ years. If you want the best Kubernetes integration, you can either use CRI-O or the CRI plugin from Containerd too. Maybe the CRI plugin might have an advantage because they have the Docker Containerd code base, and they've been around longer. If you want some good performance, you can use something like Kata. If you want even better performance, you can use anything with Runc or Rocket. Both of them are written in Go, so they're pretty fast. And if you want the best performance, you can use crun, or you might have to wait until it becomes widely available. If you have a mixed Kubernetes and Mesos environment, just like we do at Branch, you might stick to Docker and Containerd because it's supported by both environments, by Mesos and Kubernetes. If you have a lot of big data type of applications like Spark and Flink, you probably want to use Mesos with Docker Containerd too, not with Mesos containers, but Docker Containerd. Kubernetes just released a Spark controller, but it's still in the works. It's not very production ready. So, but if you want to use production-ready Spark or Flink, you might stick to Mesos. So if you want good security and isolation, anything with Runc or Rocket might have a little bit of an advantage there with trusted platform modules, TPMs. But Runc also provides all the different nitty-gritty like AC Linux, SECOM, AppArmor, Linux capabilities, and so forth. And if you want the best security, you might want to wait for the first release of Kata containers. So what does the future look like? So I see more and more of these runtimes converging into OCI. And not only OCI, but all the other standards like Container Networking Interface and Container Storage Interface. As far as CRI is concerned, Kubernetes will use that as a default to talk to all the different container runtimes. Then Docker will adopt the CRI plugin for Kubernetes to talk to it. So currently, with the current Docker implementation, Kubernetes is more like it directly talks to the Docker daemon, but then it will move more towards CRI and CRI plugin. And CRI-O will continue as an alternative to Docker, very similar to Docker Containerd. Both of the projects have committee members in the OCI committee. So potentially, maybe these two projects might merge in the future, but it's not very clear now. And as far as Kata is concerned, they'll continue developing the runtime and to provide more security and more isolation. And I expect all these different runtimes to support future Linux kernel capabilities or features that allow you to isolate your workloads to run more isolated containers and more features for containers. So in the end, all these runtimes running towards OCI, and here are some resources, and that's about it.